So based on this explanation, the Fermi energy is the largest possible energy of the electrons inside this in this K space, and then Kf is the largest wave vector possible. But when we think about the effect of temperature, so as I mentioned, if we think about some sphere in the K space, it means the electrons are staying inside the smaller Kf but K values. It's 100% electron occupied the state, but if it's outside, it must be 0%. So no electrons can stay outside of this distribution of this K sphere. But as we've already studied, due to the thermal effect, this couldn't be possible because of the Fermi distribution function. So always Fermi particles are dominated by the distribution function called Fermi-Dirac distribution, which is again F epsilon for exponential epsilon minus mu k t plus 1. So as we've already studied, even outside of this maximum energy, there's some probability that electron can stay outside of this epsilon f or kf values, because as you can see that when we think about the Fermi distribution function, looks like this. So Fermi distribution function surely changes drastically somewhere around mu. But if the temperature gradually increase, so meaning that compared with the excess energy or less energy to mu is comparable to the kBT, which is the thermal energy, this sudden change of the distribution gradually kind of like distorted. So it's not going to be a sudden change or more continuously connected, meaning that even for the smaller energy than mu, the not 100% of the states are occupied by electron. And on the other hand, even for a higher energy than the mu, some percentage of the states are occupied by electrons. So this is the thermal effect. Okay. And then now we need to understand the density of states. And based on the equations and this, so here's a relationship between the number and energy, right? So number of states and energy. So you can change this equation by solving n, right? So that gives n is equal to pi squared 2m. You can solve this way in the exercise too. for yourself. Like this. So this is the number of states allowed in the energy epsilon. And density of state is defined by the number of states per energy, meaning that how many energy states are possible in some region of energy. And from the definition, it is a derivative of n by epsilon. So you just differentiate the equation 7 by with respect to epsilon. It gives v over 2 pi squared 2m h squared. So now you can calculate how many energy states are available for electrons at each energy level.